So this topic is to look into more detail about the electric motor for the EV. We have two sessions, number one and number two. So today we go for the number one. So certainly in this topic, we're going to discuss some basic motor. The basic motor means the DC motor, which is really conventional motor. I think everybody learned some DC motor in the past. In here, I go for some basic parameter, basic principle. And then we're also looking into some PM DC motor, which is also very common. And then we're looking into some basic equation and also application to EV. If you study the electrical machine in the undergraduate, which I don't think you have, but I'm going to teach it in next semester. I mean in the autumn 2025. But here it just gives you some really basic about DC motor. Maybe you learned the DC motor in the past. Have you all learned some DC motor? Okay. So first of all, some target question will be, so which one motor is most commonly used in EV? What do you think? Here. The thing is high performance. They like high performance. High power. And then why can the EV motor perform power regeneration? So power regeneration is one thing I have been talking about. EV is good because it can able to provide power regeneration. Why motor can become power regeneration? Do we need to put enough generator in the EV to provide power regeneration? Or we can just using the motor to do the job without additional generator? What do you think? When EV going down the hill or braking, it's so-called power regeneration. How we do that? Do we need to put a generator to regen energy? Or what? Any comment? What do you think? What's power regeneration? I think you all know, yeah? Power regeneration for EV. You all talking about it. What is power regeneration here? How do we do that? This gentleman, what do you think?
Yeah, I don't, as far as I understand, I don't think there needs to be a generator. It uses the motor itself to basically engine brake, and you can return power back to the battery.
Yeah. How about you see? You want to comment?
So one thinking is that there's energy being converted from potential energy to the like electrical energy, but what I'm thinking is that you have to store it somewhere, right? Like you can't just have the because they're just like it needs to go somewhere. So I'm thinking more like intuitively you store it somewhere.
Okay.
I don't know if that's
Well, imagine we say we've got EV. We drive the EV up the top of the mountain. We store some potential energy there.
Yeah.
When you're going down the hill, of course, the energy has to go to somewhere and you store them in a battery system. But anyway, the motor itself is also the generator. So all the motor can become a generator anyway. We don't need a separate generator. So that's the most important part for EV. We don't need an additional component. You can do everything. Sometimes the efficiency for both motoring and generation is the same. Really good. So, and then which mode is the best for EV? I think it's really subjective. We don't have any fixed answer. Some people like PM synchronous. I myself like SR motor. Because SR motor is low cost, cheaper, and you can publish more journal paper. You see, we are professor, we need to publish paper anyway. PM mode has been there for 100, 200 years. I can't publish any more journal paper. Nobody will say it's good. But SR mode only really few journal paper. So that's an area for research and development. Fault tolerance. I always say SR mode has fault tolerance because you're able to, after a while, the connector is still able to work. So that's why fault tolerance is also important for EV. And how do we drive motor? We need some kind of this controller inverter. Later I'll show you how they're going to work. And then how do you think a future motor? We're not quite sure yet, but I think still a lot based on PM. But how we modify PM become much better, we're not quite sure. Maybe PM integrate with SR switch reluctance. Anyway,
So today we're going to go for a number of content, including motor, DC motor, PM motor, AC, induction switch reluctance. We go for a number of topics. So basically, you can see that there's an EV motor drive system. You got DC bus, which is a few hundred volt, probably 800, 600, 500, depending on your vehicle. Then we call it DC bus. And then we tap the energy to the inverter. We all know the inverter is DC to AC. And then inside the inverter, we also including the motor drive system. And then we need to control them. So control them, we have a central computer, we call VCU, vehicle control unit, just like a computer to control. So that's it. Very straightforward how the system look like. So the inverter itself also consists of all the driver, controller, or internal control unit for the inverter. They all included inside inverter. Today, when you buy any inverter, they are just like a box. All you do is there's some control wire through your vehicle computer, maybe the campus. And then you also put in a DC bus to the inverter, and then there's the whole system. Sometimes these two may integrate together, become a single unit. So that's why today when you open up EV, probably you can't see anything. They all just in power module. You can't see any wire. You can still see some wire, but probably it's so much different from what you see in a gasoline car. Open a gasoline car, you got so many components, but not in EV anymore. We're all using this kind of the new fabrication technique. So that means for motor drive, you can see that we got the load that means is our wheel, our kind of the transmission output system or mechanical outputs. And the inverter is the one we mentioned just now, is connected to DC drive, and the inverter itself is trying to convert the DC voltage into suitable AC voltage in terms of the frequency and also voltage and current to the motor. The motor itself basically provides your motoring. The motoring is usually controlled by VSD, variable speed drive. Variable speed drive is a kind of the name we put to the inverter, able to control motor different kind of frequency or speed or the voltage. So that's a already really mature technology. Good thing is this all the motor we can able to use VSD to drive them in either direction, forward or backward. So that means we don't need to change gear. So that's really straightforward. Just control the so-called the angle of the rotation. So basically how the motor drive will do. But bear in mind, we got 4 quadrant control. That's a really important concept in electric vehicle or in many of the motor drive system. And if you learn any EV, you need to know about 4 quadrant of the control system. Basically, the quadrant number 1, I think important now. Probably many people have learned it. Anybody studied the motor, you should have learned the 4 quadrant, right? Have you learned that? I think in your undergraduate year one or 2, right? Yeah. And have you learned that? How much gentlemen? No. Yeah. So for instance, if a vehicle going up the hill, then you need to drive the vehicle to forward motion. So that means your torque should control motor torque to forward, control motor speed to forward as well. So that means 4 is so-called the quadrant 1. That's the most common operation. All the vehicles should be doing that. Then, so when the speed, another scenario will be if now go up the hill, then your you try to have forward motion to the vehicle. Then, however, if your vehicle is now, because it's going down the hill, it is now in a slope. So the vehicle will therefore If you don't energize it at the moment, you can see that the vehicle itself will fall downward. Falling downward, that means more look like we got the energy, pick up the potential energy back into the battery. Somehow we call it the power regeneration. Once you go down the hill, when potential energy, we turn it back. So you can see that in here, the motor will put it from battery energy, go to the motoring, pick up the potential energy. But once we lock energy, we don't tend to energize it, the vehicle will tend to slip downward. The potential energy will return to the battery. Then you give you the so-called reverse braking. That means the vehicle will tend to brake in the reverse manner because potential energy pull it downward, try to brake the vehicle. Simultaneously, the energy to the potential will return to the battery. Then in this case, we do have the power regeneration. Then there's another scenario will be if the vehicle is going down the hill, then we energize it to down the hill. Because the potential energy is also pulling the vehicle down the hill, so then the potential energy will try to return to the battery as well. So in this case, if moving down the hill, potential energy also moving downward, and this energy will have you return to the battery. So we do have a potential energy helping to do the power regeneration. So you can see that the vehicle, although it's going down the hill, because potential energy will return, the vehicle going down is slightly slower because some energy is to return back into the battery system. So that's why we can still able to see some kind of the braking because due to the energy return to the battery. But if in this case, if you don't want to do that, you want to same kind of follow, you can help shut down the battery connection. The vehicle will still going forward without any feeling of the braking. So once you connect the battery to braking, we still have the power regeneration due to potential energy delivered downward into the regen. Another scenario, quadrant number 3, will be this one is moving forward, but if now you reverse into reverse speed, move the vehicle reverse back up the hill, then you can see that you are not the friction, one friction, not many friction. One of the force will be downward force by the gravitational force. And then your vehicle has to reverse back up. Then in this case, this reverse force need to against all the downward force, such as mg sine theta, all these downward force. So that's why this just like the normal motoring. This is the conventional motoring, but this is reverse gear motoring. We call it the quadrant number 3. So the normal motoring of an EV or whatever is a motor or not, because quadrant number 1 is the motoring. Quadrant number 3, we call it the also motoring, but reverse direction. These two, just like forward and reverse, are most common driving method, forward and reverse. But because we change the direction, then we just call it the quadrant number 3. So you can see that the direction here, the top, we are moving forward. The speed, we are also moving forward, quadrant number 1. But if we change the motor direction, we can force the motor to reverse up backward by still doing the motoring because it's all the energy by motor giving out to provide the mechanical movement of the vehicle. It's not doing any power regeneration. So that is still just simple reversing, simple forward. So that's a 1 and 3 are two most common configuration for motor. But however, due to the power regeneration, then these two are able to transfer its dynamic energy or potential energy back into the battery.
then we call the power regeneration. One of them is called the reversing, because the speed and the torque are in different directions. So usually you can see that if the speed and the torque are the same direction, then it must be the motor. Because this is going forward, this one is going backward. The vehicle just reverse gear going backward to against all the pulling force. So this vehicle also going upward and try to against all the pulling force due to the gravitation. But once the vehicle going upward like this, then if suddenly you don't press the button to give away energy from your motor joint, the gravity will pull the vehicle downward. Then in this case, you can able to absorb some of the energy. But however, in this case, the vehicle speed will gradually go down, will be reducing until become zero speed, and then you maybe go back to the reversing. So this more look like, in this case, you're driving a vehicle upward, you're putting energy from the battery to your wheel. And then next, you stop putting the gas. Then the vehicle will be pulling downward by the gravitational. The speed will be reducing. Gradually reduce during that time. The vehicle still slightly going upward, but reducing the speed until it becomes zero, or maybe reversing. So this time it looks like reversing braking the vehicle, and then also provide you the power regeneration. So basically, we provide us about 4 quadrants of the EV operation. Even though if you look at many of the motor books, they also have the 4 quadrants of operation. So depend on the motoring or reversing. So that's basically about some of the interpretation, how we understand about the motoring and braking. This concept is not difficult, but you need to have a new concept of mind, how to understand the motoring and the movement of the vehicle, so that you know how we can understand vehicle become motoring or power regeneration. But when you design EV, you don't need to consider all this. But on theory, on the bookwork, many of textbook and many professors like to talk over this kind of the 4 quadrant control system. But anyway, when you control the inverter, like this kind of inverter, you still need to know how to turn on which devices to force the motor to forward and backward and power regen. For instance, when you control the motor forward, like this, if suddenly you turn off all the transistors, then the vehicle will still try to reduce the speed because it still has some momentum going forward. But the gravity will pull you downward. So then it looks like we are now using the gravity to power regen to store, return some energy, reduce the speed back into the motor. So we'll show you how to use transistor to control this tool. Similar, then reversing. A vehicle putting in a hill, then you use reverse gear to move the vehicle backward. Like that. So that means the torque will become reversed, the speed also reversed. And then in this case, we suddenly turn off the power source or turn off the energizing transistor. Then the gravity will also pull the vehicle downward. In this case, it's good. It more look like we now charging back the energy into the vehicle. So there's a totally 4 different kind of the scenario. We commonly appear in many of the literature. So here, the basically talk about different scenarios. In the first quadrant is most common operation. when vehicle is forwarding and the driving power from battery provide your vehicle in a forward movement. Then in second quadrant, when your vehicle is still moving forward, then you release the acceleration gas, and then the low power provided from the battery to the motor. But the vehicle still has its own inertia. Then that inertia will not allow the vehicle to stop instantly. But instead, the energy, so-called the inertial energy, dynamic or potential energy for vehicle, continue the motion, but gradually return it back into the inverter, through the inverter to the battery. Then you can see that how to do that, you just need to release the gas pedal from the accelerator, then this will automatically happen. Then that will go back to our second quadrant of the control. So later on, we show you how that can be done by a simple motor drive system, how that can be done. Then the third quadrant is the same as the first. You just put all the cars going reversely. And the fourth quadrant is also the same, but just reversely, you release the gas pedal so that allow the vehicle to gradually reduce the speed and return the dynamic energy back into the battery. So that means the first quadrant is the D mode, just like a vehicle in the D drive. And the third quadrant is the R mode in the reverse mode. And then the other two, fourth and third quadrant is just like the power regeneration. When a vehicle is to lock the gas, the energy will return to the battery. You can feel that the vehicle is slowing down. That will be in the fourth quadrant and the third quadrant. So that's all. So four quadrant control is really common in all the vehicle, in all the motor anyway. And then next thing we discuss about the power efficiency. The power efficiency of motor, and all the motor for EV, the efficiency is really, really high. Usually will be 90 something. At least more than 90 will be common. For more than 30 kilowatt motor, 90%, 95 is really common. Some of them may be equal close to 96, 97. But for low power motor, like less than 3 kilowatt, like some golf car, or maybe some small boat system, the efficiency will be quite low, 70 to 85. But the power regeneration is not the same efficiency. Power regeneration efficiency will be less than the motoring. So usually you can see here 60 to 80. Even though a motor is 90% forward efficiency, the power regeneration will be less, only about 80 or maybe less. It all depends on how the motor is being designed. Will the design cater for more motoring efficiency or more power regen efficiency? Of course, maybe design EV will choose those that have more efficiency for motoring instead of the power regeneration. So you can see that the battery voltage more or less are quite constant. Although we charge and discharge the battery voltage varies slightly, but basically we can consider battery will be more like a fixed voltage. Then when you do the power regen, then your motor engine will return to the full controller to the battery system. So that's a constant voltage. How you ensure the engine inflow to a constant battery source will depend on its control capability. If you allow more current flow back to the DC source, then that's a job for the controller. So that's why this controller, you're able to perform how the braking or power regen braking look like. So that's also one of the capability. Another feature, you can see that the motor torque usually relate to the current. Sometimes proportional, sometimes proportional to current square, depending on which type of the motor.
So usually you can generate higher current for the motor because you're able to provide higher motor torque. So these are proportional to each other. In many cases, we tend to control motor torque by using a current mode controller. So most of this kind of control system, they may measure the current in here to use the current mode control to control that. So now then, let's discuss briefly about the DC motor system. We use the DC motor because that's one of the really common motor drive system. I think some of you may learn them in the undergraduate. So here we show you, basically we got two major type of the DC. One is called a permanent magnet DC motor, PM, and another one field. One field, that means we don't use PM to generate the magnetic field. We use winding for the one field. The winding will generate the field by itself. So that means you need additional field winding for the generation. The field winding can be excited by a separate voltage source, or they can excite it together with the armature current. Then PM, because it's using PM magnet, so that's why there's a low field winding. The thing is, PM, because fixed one, the field will be fixed. You cannot control the magnetic field. But for the other type, for the one field, because you are using separate inductor to create the field, you can control the field. Later on, you can see that if you're able to control magnetic fields, you can have more flexibility to control the motor operation. So that's why in here, we can see that PM do have advantage, but we have difficulty to control them, especially when we want to overdrive the motor. There's some technique in the motor drive system we call them the overdrive. We tend to operate the motor at a very high rotational speed. In this case, we need to give up on the torque because with high speed, we cannot have so high power. So we usually will reduce the torque. So with high speed, the motor torque will be reduced. So simultaneously, we have to reduce the magnetic field current to help the motor torque for reduction, having some current. Because if the current is still too high, then you overdrive the motor anyway. So we have to reduce the current or we reduce the field. But now then, for one field system, you're able to control the magnetic field. But for PM, we cannot. So PM motor, in a way, we may have a less advantage. In a way, we control the motor speed to be really high speed. That do have some disadvantage. So later on, we'll show you some chart, then you understand the advantage against each other. So here we'll show you really basic one quadrant drive system. Maybe you can see this diagram in the past. So let's explain what it is. So we got DC source. Usually one quadrant control, we only consider one directional. We got transistor, we got one thing here. So that means when we energize them, turn on, this voltage appear across the motor winding, energize them, then that's why motor will get rotation. But if you want to control on off the motor, if you turn off here, then this current of the motor is an inductor winding. So you cannot stop the current straight away. If anything have an inertia, including this current. So this current have to loop across this style to continuously. We call it the freewheeling, wheel the current in this loop. Why we need to do that? As I mentioned before, we cannot stop any current instantly. If you stop instantly, then it will cause you high spike voltage. You will damage all the winding, damage transistor. So we need to let the current to loop somewhere. So in here, we are not putting new energy into the motor. We just leaving this motor energy to loop by itself. Probably the speed will still slow down because the resistance loss in here. But we're using this method, we energize them, give them power to drive, and then we slow down or slowly down constant speed, or we are using its own resistance to slow down the speed. So that's first quadrant control. We're able to control motor forward motion. In here, we have not considered any power regeneration. What power regeneration? Regenerate the current will return back to the battery source. But this current, without doing anything, only looping here.
So it's no power regeneration, only first quadrant of the motor drive control. You get that? I just worry about this part may be too difficult for some of you if you haven't studied the electrical circuitry. Are you all okay? Yeah. Good.
I see.
How about you? Still,
I just had a question on, so when the current continues to run through the diode, like how long is, I guess that,
Depends. Depend on how much resistance here. Or depend on the real vehicle. You see a vehicle there, there will be at least many power losses, not only circuit loss. Your tire have friction, your air has some friction. So all this will start to slow down your vehicle, slow down the current in here. So this current will support will be air friction, tire friction, circuit resistance. So you eventually slow down. So, but using this method, you can on off to control the motor speed. Turn on high speed, turn on low speed. Let me draw you some diagram. So when you energize it, the motor will go to here. See the speed. When you turn off, you go down here. The next, you find the speed is too low, then turn on, turn off. So, and then you can see that the speed roughly about this region. So we use this method, turn on, turn off, we can control the motor speed at certain range. Of course, in here you can see how come the speed ripple. But in fact, we use really high frequency switching. So that means actual happen in here will be like that. Still, we really high frequency. So probably you cannot feel any ripple on the top because we use this on and off to control the speed variation in this range. That's so-called the speed control. Yeah, if you keep turning on, if you don't have this method, then the motor will go to something infinity speed. That's impossible, right? So all is doing in here to control the motor speed. So that's the basic concept how we control motor speed. All right. Any other questions? Have you learned this kind of the motor drive?
Not a long years.
Long time.
Long time.
Yeah, but you're still able to.
Yeah.
Yeah. Okay. Stop me if it's something you're not quite sure, and then I can change the way to present it. So that's how it looks like, right? Turn on, the current go up, and turn off going down, so you can able to control the motor current in something. And then you can see when turn on, the current go to the transistor, turn off, the current go to the diode. So that's how we manipulate this turn on and turn off period to manipulate this current, which are even though the speed to have certain location. So basically how we using this kind of transistor technique to do the job. Right. Then this period, we call them the switching period, just like I mentioned about say 20 kilohertz, 10 kilohertz, 100 kilohertz is this kind of period. You can see that if you want to reduce this ripple to be small, then when the current ripple is small, because I mentioned before, torque and current are proportional to each other. For motor drive controller, I want the torque ripple to be small so that we don't have any vibration. So now that if I use very high frequency, this ripple can become smaller. Just like in here, low frequency, you got large ripple. When you use small frequency, you got small ripple. So that's why I always mention to use high frequency to control them. Right. So of course, if you want to do some math calculation, then we can do that. The turn on and turn off will be equal to the period, the switching frequency period. If 20 kilohertz, the period will be 50 microseconds. How much turn on and turn off? We can use an averaging technique to get the actual voltage coming out from the transistor. So that means in here, this equation shows us what's the average voltage will go to the motor. It's some kind of the proportional equation. That means if you want to calculate the voltage across here, When I turn on, the voltage are called CM equal to battery voltage. When I turn off, become 0 volt in here. So these two average will become the actual voltage or the average voltage across the motor. So that's how we calculate. Sometimes we like to calculate how much is the average voltage to the motor drive system. So that's basically a very simple proportional equation. You can calculate it. So that means we can adjust the duty ratio, or so-called the inverter duty ratio, to control on-off time, to control the motor voltage. Hence, we can control the torque and control motor current. So first tutorial, let's see. We want to calculate DC level of the motor, IM. How are we going to do that? So we are assuming the motor is 20 kW of power, the battery 400 volt, the duty ratio D equals 0.5. How much is the current? And if the efficiency is 90%, what is the battery current? Very simple calculation. Have a quick look for 1 minute, then we'll talk about the answer.
And then P equal to IV. So I that going to be our V, which is like 20K kilowatt divided by 400.
Yeah, you know the power for the motor?
Yeah. Motor power is
You know the
20K, right?
voltage. The voltage will be 400, right? Here, the battery. Then you can therefore calculate.
$5,000.
5,000 M. Won't be that much. No,
No, sorry. Sorry. 50 ampere.
Let's see the my proposed answer.
So the motor power is 20 kilowatt. Then because we are switching at 0.5 duty ratio, this comes kind of averaging 400 volt motor by IM, so motor current should be 100 M. Then this motor power, if I assure 100% efficiency, or the motor power will equal the power for the battery. Then battery will be battery 400 volt, current of battery is going to be calculated. The motor power 20K, we can carry battery equal 50. You can see that these two ratios also by a double because of the duty ratio is 0.5. And then that's an ideal case for A and B. But in some cases, if you do have an efficiency problem, for instance, you've only got 90% efficiency. That means for all the battery energy, only 90% can deliver to the motor 20K. Then if you calculate the battery will become 55.5 amp. That's it. But it's not difficult. It just show you some really basic how we can operate a DC motor under a simple battery system. All right, any questions? So another motor topology we try to introduce to you will be so-called the one-field DC motor. You see just now the PM motor, we got separate magnet for the PM. But if you don't have any PM, then the magnetic field is generated by a coil. We call it one field. So this kind of the winding, called the one field winding, provide you with the magnetic field. You can use separate excited another power source to provide the magnetic field for the winding. So on motor like that, they got armature there, and then separate for the field, magnetic field. Usually this current for the field is not that high current, only small amount of current, only talking about 10%, 20% of the main winding. But to do that, we can either set the shunt, that means we pair them all up. When you use the shunt connection, that means this field winding voltage equal the input voltage. So we have less contributivity to this field current. And then sometimes they may you also using series connection, that means this armature current, motor armature current, and the field winding current is the same, called the series. So probably that may not be a good design. Even once we change the motor voltage, this will be changed, or we want to change this thing, the motor voltage also be changed. But sometimes we may use both a portion of the winding in here, in shunt, a portion winding in here, in series. So also become a possible connection line. But many cases, we do prefer to have a separate excited. We can use separate circuitry to control the field. That will be much easier. Because in some many cases, we do need to control the motor field. For instance, we call them field weakening. When we want to overdrive any motors, then we have to use the weaken the field so the motor can even run at higher speed. So that's another technique. We call it motor drive, call it overdrive this kind of system.
Another question.
Yes, please.
So I like fill out that when you say mini project presentation, I fill out for week 2. So
We feel for week 2?
yeah, for this week. So when should I present?
Oh, I didn't know that. So you can present now. Yeah,
Yeah, I can.
yeah. Okay. So what is your top topic?
Talking regarding EV models and brands.
Okay,
parts.
Then I did remember, okay, probably now we don't have too much time, then you come over to present it. Then because I guess you want to make use of the HR credit, higher bonus mark, right? Fair enough. So let's stop here. And then we continue next week. Then you come over to the stage to present, please. Then I end the